Hello students, in this video I'll be explaining the concept of formal charge and how it's applied to Lewis structures. So the idea of formal charge is based on the assumption that electrons in a covalent bond are shared equally. What this implies is that if there is a covalent bond between two atoms A and B, and we know that a single covalent bond is made of two electrons. Uh, this means that these electrons are shared equally between the atoms, which we know is only valid if the two atoms are of comparable electronegativity, but this is not always the case. Anyways, let's just go along with the assumption because this has its own use cases. So how do we actually compute the formal charge on an atom in a molecule? Basically, we take the difference of the number of electrons which were there in the valence shell of the atom before bonding and the number of electrons which are there after bonding. Now we know that when a bonding happens, on the atom there are either the bonded pair of electrons, so you have bonded electrons which were involved in covalent bond, and then you have the lone pair or the non-bonded electrons, right? So that means if we can split this, the difference becomes formal charge equals to valence electrons on the atom, right? Which can be directly deduced from the group number, minus the non-bonding electron and minus half the number of bonding electron. Why half the number? Because we know that the other half comes from the different atom. So it's only half the number of bonding electrons which actually belong to the atom that we are concerned with. Let's just understand this formula in view of an example. Let's just calculate the formal charge on all the atoms in water. The first thing we need to do when we have to calculate formal charge is we need to be able to draw the Lewis structure of the specific molecule or the species. So let's just draw the Lewis structure of water, which we know looks like this. Okay, so let's calculate the formal charge on hydrogen. So the formal charge on hydrogen is the valence electron on hydrogen, which we know is 1, right? Minus the number of non-bonding electrons, and we know there are no non-bonding electrons on hydrogen, so that is 0. Minus half the number of bonding electrons, so we know that the hydrogen atom has made one covalent bond, so there are two electrons there, so this becomes 1 minus 1, which is 0. All right, and we know that the other hydrogen atom is also in a similar situation, so that means the formal charge on the other hydrogen is also 0. Let's calculate the formal charge on oxygen now. So we know that formal charge on oxygen shall be equal to the number of valence electrons that are there in oxygen, which is 6, minus the number of non-bonding electrons. Now we can see that there are two lone pair of electrons on oxygen, which means it has 4 non-bonding electrons, right? Minus half the number of bonding pair of electrons, as we can see that it has made two covalent bonds, which means that there are 4 bonding electrons. Again, notice the term bonding electrons, not bonding pair of electrons. So it's half the number of bonding electrons, which is half times 4. So we have 6 minus 4 minus 2, which is also 0. So notice that the formal charge on all the atoms is coming out to be 0, and some of this is also coming out to be 0. This is an excellent test to validate your Lewis structure. The sum of formal charge on all the atom in a specific molecule or species shall be equal to the overall charge on it. In this case, we had water, which is a neutral molecule, so the sum of formal charges also comes out to be 0. But now let's take another example where the sum of formal charges will not be 0 because this is a molecular ion. So we have nitrite ion NO2 minus here. All right. Now in the previous tutorial we already deduced the correct Lewis structure of nitrite. So let's just go along with that in the interest of time. And this was the Lewis structure that we deduced. All right. So let's now calculate the formal charge on all the atoms in the species and then validate whether this particular Lewis structure is correct with respect to formal charges. All right. Let's first calculate the formal charge on this oxygen. So the formal charge on this oxygen shall be equal to the valence electrons, which is 6, because oxygen is in group 16 and all group 16 elements have 6 valence electrons, minus the number of non-bonding electrons. Now we can see that there are 3 lone pair of electrons, so there are basically 6 non-bonding electrons, right? Minus half the number of bonding electrons. So you can see that this oxygen here has made just a single covalent bond. So that means there are only 2 bonding electrons. So this comes out to be 6 minus 1. So the overall formal charge comes out to be negative 1. All right. So for this particular oxygen atom, the formal charge comes out to be negative 1. Let's now calculate the formal charge on the nitrogen atom. So nitrogen is in group 15, and we know that being a group 15 element, its valence electrons should be 5, minus the number of non-bonding electrons, which we can see that there is just only one lone pair, so that means only 2 non-bonding electrons. But we also see that this nitrogen has made 3 covalent bonds, right? We are not making a distinction between sigma and pi bonds here. We're just considering the total number of bonds here. So this nitrogen has made 3 covalent bonds. So the number of bonding pair of electrons is 6. So we do minus half times 6. So this comes out to be 5 minus 2 minus 3, which is 0. So the overall formal charge on the nitrogen comes out to be 0. Let's just write that. And now let's calculate the formal charge on the oxygen atom on the right. So here again, the valence electrons are 6 minus the number of non-bonding electrons. We can see that there are 2 lone pairs here. So there are 4 non-bonding electrons minus half the number of bonding electrons. We can see that this oxygen has made a double bond here, which means that there are 4 bonding electrons. So minus half times 4, and this also comes out to be 0. All right. So the overall formal charge would be the sum of these formal charges, which is minus 1 plus 0, which is minus 1. This is how we validate the correctness of a particular Lewis structure. Okay, so the sum of the formal charges should be equal to the overall charge that appears if it is a charged entity, and should be 0 if it's a neutral entity. So, what is the application of formal charge, especially to Lewis structures, to different Lewis structures which contribute towards resonance? Basically, so far we have come across resonating structures which were equivalent, which looked alike, and so their contributions were the same. But sometimes we have different Lewis structures which contribute towards the resonance hybrid. In this scenario, we have to actually choose the most stable Lewis structure which makes the greatest contribution to resonance. And we can choose the more stable structure by using the idea of formal charge. So there are, in order to identify the most stable Lewis structure, which makes the greatest contribution towards the hybrid, there are three things that we must keep in mind. First of all, the formal charge on the atoms, that means all the atoms, should be close to zero. Naturally, if the species is a charged entity, there would be atoms which would have a charge, but they should be as close to zero as possible. Number two is that there should be low separation of charges between atoms. What this means is that there should be avoidance of having a center of positive and negative charges within the same entity, as separation of charges requires energy, and this increases the energy and decreases the stability of the entity. And the last rule that we must follow is that the negative charge, that is the negative formal charge, should be assigned to the more electronegative atom. Let's see the application of these rules to two examples. So let's first draw some Lewis structures for sulfite ion SO3 2-, and then using the rules of formal charge identify the more stable of those Lewis structures. All right, so let's use the same rules that we followed in the tutorial. So let's first identify the total number of electrons. We know that sulfur has 6 valence electrons. Oxygen also has 6 valence electrons, and there are 3 of those. So there are 3 times 6 valence electrons total contributed by oxygen. And then there is a 2- charge, which means 2 extra electrons. So if we count the total number of electrons, this is 6 plus 18 plus 2. So there are a total of 26 electrons that we need to account to. All right. So let's again follow those same rules. We place the central atom. We place the peripheral atoms around the central atom, and we join the central atom to the peripheral atom by covalent bond. So out of 26 electrons, 6 have already been accounted for by making these single bonds between sulfur and the 3 oxygens. Then we put lone pair of electrons to satisfy the peripheral atoms. So here 3 lone pairs on each oxygen, right? And since there are 3 lone pairs, which is basically 6 electrons on each oxygen, that would mean 18 electrons have been accounted for. So that just leaves us with 2 electrons, right? And as per the rules we have followed, we can have a lone pair of electron here, and that basically solves our problem, right? So all the 26 electrons have been now accounted for, and this is one of the Lewis structure of SO3 2-. But the question is this the only Lewis structure? And if there are other Lewis structures, is this more stable or less stable than the other structures? So let's try to verify the fact. Now, before moving ahead, it's important to remember that again the central atom in this case is a period 3 element, and period 3 element can extend their covalency beyond 4. We know that they can expand their octet. Okay, so let's first calculate the formal charge on the 3 oxygens and sulfur. Now all the 3 oxygens here are similarly placed, so if we calculate the formal charge on any of the oxygen, that should basically tell us the formal charge on all the 3 oxygens, right? So oxygen has 6 valence electrons minus each of these oxygens has 3 lone pairs, which means that there are 6 non-bonding electrons, and each of these oxygens has one covalent bond originating from it, which means the number of non-bonding electrons are 2. Alright, so that means each of these oxygens has a formal charge of -1, right? Let's just write that. So each of these oxygens has a formal charge of -1, and you can guess what will be the formal charge on sulfur in order to account for the 2 minus charge, but let's just calculate that anyways. So for sulfur we have 6 valence electrons minus, if we see that there is only one lone pair, which means that there are only 2 non-bonding electrons, right? And there are 3 covalent bonds around sulfur, which means that there are 6 bonded electrons. So the total formal charge comes out to be +1, right? So this all adds up and the sum of the charges comes out to be 2 minus. But if we looked at the rules on the previous slide, the first two rules are not quite obeyed in this scenario. First of all, there is no atom here which has a formal charge of 0, right? And the second is that there is a separation of charge happening. So we have positive charge appearing on one atom, and then we have negative charge appearing, which kind of elevates the energy of this structure. But then the next question is that, okay, if this Lewis structure is not that stable, can there be a more stable Lewis structure? And the short answer is yes. Now, in order to get the more stable Lewis structure, what we do is we use one of the lone pairs on the oxygens to make a double bond with sulfur. Now, for a moment, you might think, oh, but this is violating the octet rule. And that is true. But then sulfur, as I said before, is a period 3 element, which means it can extend its octet. It can extend its covalency beyond 4. So if this happens, the new sulfite structure is probably going to look like this, right? Okay, so now comparing the older structure with the new structure, we see that these two oxygens, the ones here, they are in a similar position. So that means their formal charge still stays -1, right? Because their number of bonding and non-bonding pair of non-bonding and bonding electrons are virtually the same. But the position has changed for the left oxygen and the sulfur. So let's calculate their formal charges. Let's first calculate the formal charge on the oxygen on the left. So here we have 6 valence electrons minus the number of non-bonding electrons now have reduced to 4 because there are only two lone pairs of electrons. And then this oxygen is making a double bond, which means that there are 4 bonding electrons. So we do minus half times 4, and this comes out to be 0. So unlike the left structure and unlike the other oxygens in this entity, the formal charge on this oxygen is actually 0. Okay, and let's now calculate the formal charge on the sulfur. So now on the sulfur, you have 6 valence electrons again, and there is a single lone pair, which means that there are 2 non-bonding electrons, and we can see that this sulfur is making four covalent bonds. As you can see that there is a double bond now and there are two single bonds. So there are four covalent bonds, which means that there are four pairs of bonding electrons, which means that there are eight bonding electrons. So minus half times 8. So that means 6 minus 2 minus 4, which is again 0. Alright, now you can see why this particular Lewis structure of sulfite is going to be relatively more stable than the structure on the left. That's because number one, unlike the structure on the left, there are some atoms here which have a formal charge of 0. And number two is that because there is no positive charge on any of the atoms, there is no charge separation. And because there is no charge separation, the overall energy of this entity is going to be lower. That being said, this doesn't mean that the structure on the left is incorrect. It just means that the overall contribution to the resonance hybrid by the structure on the right is going to be more than the structure on the left because that is more stable. If you do not understand this part, I request you to please pause the video, try it again, or maybe even review it till this part. Let's move to the next example if this is clear. Let's now attempt to draw Lewis structures of N2O and let's see where that leads us to. So in N2O we have, let's first calculate the total number of electrons. So nitrogen has 5 valence electrons, so that is 5 times 2, and then oxygen has 6 valence electrons. So the total number of electrons that need to be accounted for is 16, right? So we now have nitrogen as the central atom and the other two nitrogen and the other nitrogen and the oxygen as the peripheral atom. And just as before, we make two covalent bonds with the two peripheral atoms. So that accounts for 4 of these electrons, right? So we now left with 12. And now what we do is we have the valence, we have the non-bonding electrons, the lone pair of electrons in the peripheral atom. So we have 6 on this one and 6 on this one. All right. So that would mean total of 12. So that means all the electrons have been accounted for. But then we can clearly see that the octet rule is not obeyed here. So we do the next step as we understood in the previous video, and that is to transfer the lone pairs to make a bonding pair. All right. Now in this case, the final structure, the final Lewis structure of N2O is probably going to look like this, right? But again, the question is this Lewis structure stable? Let's try to calculate the formal charge on all the atoms in this Lewis structure of N2O. So in the case of the first nitrogen atom, the formal charge is going to be 5, which is the valence electron on nitrogen, minus the number of non-bonding electrons, which is 4, and minus half of the number of bonding electrons, which is 4 again. So in this case, this is 5 minus 4 minus 2, which is coming out to be -1. Alright, so this is the overall formal charge on the left nitrogen atom. Let's just erase this and just write -1. Let's now calculate the formal charge on the central nitrogen atom. So the overall nitrogen, so the central charge on the formal charge on the central nitrogen is going to be 5, which is the valence electron on this nitrogen, minus the number of non-bonding electrons, which this doesn't have any. There are no lone pair of electrons, so minus 0, and minus half the number of bonding electrons. So we can see that it has made 4 covalent bonds, 2 on this side and 2 on that side. So that is 8 bonding electrons. So minus half times 8. All right. So we have 5 minus 4, which is plus 1. All right. And now let's find out the overall uh, let's find out the overall formal charge on the oxygen. So let's just write this as plus 1. Let's find out the formal charge on the oxygen atom here. So if we were to apply the formula of formal charge, this would come out to be 6 valence electrons, because oxygen is in group 16, minus there are 2 lone pairs, so there are 4 non-bonding electrons, and we can see that this oxygen has made a double bond, so there are 4 bonding electrons, so minus half of 4, so this comes out to be 0, right? So for this oxygen, the formal charge is 0. Now this also seems to be quite stable, for one reason in particular, is that the formal charges are close to 0, and in fact in one of the atoms we do have the formal charge is 0. But then we notice something strange. The third rule for formal charge, while applying formal charge to establish the stability of Lewis structure, was to see that preferably the positive formal charge should be on to the less electronegative atom, and the negative formal charge should be on the more electronegative atom, which is not true here, because oxygen is the more electronegative atom and yet it doesn't have the negative charge. So what is the solution to this problem? A potential solution to this problem, I'm just redrawing the same thing again so that we can make a comparison later. So N double bond N double bond O, and there are 2 lone pairs, right? Yeah. A potential solution, and of course the lone pairs here. A potential solution to this problem could be by having one more lone pair of electron going here, right? So that would be N, and then just leaving it with one lone pair and then a triple bond. But wait, if we do that, then this nitrogen, and we leave the structure like that, then the central nitrogen is going to have 5 covalent bonds, because there is a double bond on the other side, right? But nitrogen is a period 2 element, so it cannot have a expanded octet. So what we do is, when this bond has been formed, a triple bond has been formed, we break one of the bonds with the oxygen and transfer it back to oxygen, right? Now you can see how this would actually give a negative formal charge on oxygen, as we'll prove mathematically later. So now you're left with a single bond here, and you have 3 lone pair of electrons on oxygen. All right. So now let's calculate the formal charge on each of the atoms again. Okay. So formal charge on this nitrogen is going to be 5 minus, there is only one lone pair, that means there are 2 non-bonding electrons, minus, as we can see that there is a triple bond, so minus half of 6, because there are 6 bonding electrons. So this is going to be 5 minus 2 minus 3, which is 0. So now the formal charge on the left nitrogen atom has been reduced to 0. Okay. Now let's use the same method to calculate the formal charge on the central nitrogen. So this is going to be 5 minus, you can see that there is still no lone pair. So the number of non-bonding electrons is 0 minus, and we can see just as in the previous case, the number of bonding pair of bonding electrons is still 8. So this is half of 8. So this is 5 minus 4, which is plus 1, right? So the formal charge on this nitrogen is plus 1. And now let's see the formal charge on the oxygen. So if we apply the formula again here, so 6 is the number of valence electrons. We can see that there are 3 lone pairs of electrons, which means that there are 6 non-bonding electrons, right? And there is just a single bond, which means the number of bonding electrons is just 2. So this is 0 minus 1, which is minus 1. So you can see here that the formal charge on the oxygen is minus 1. Okay, now both of these Lewis structures are correct because both of them are satisfying the octet rule. Both of them have the sum of formal charges coming to be 0 because N2O is a neutral entity. But then the Lewis structure on the right is a bit more stable than the Lewis structure on the left, simply because in this structure, the more electronegative atom, which is oxygen, is the one that is carrying the negative charge, not the less electronegative nitrogen. So I hope these examples have clarified how the idea of formal charge is applied to establish the stability of Lewis structure. I hope you found this useful. Thank you.